would like to take a couple of extra minutes to say that I am very, very happy to be here and to congratulate Volker. So Volker has been my first postdoc supervisor, postdoctoral supervisor. But I have to say more than that because actually I did my PhD thesis without an advisor. So when I finished my PhD thesis, I didn't have any recommendation letter. So it was very difficult to proceed. And I wrote to Volker, and as Miguel said at the dinner, he was really ready to reply to my email, and he didn't hesitate to invite me in Mainz. I remember May 2001, and he asked me to give 6 talks in 1 month. So it was really tough. And then he promised me half of a fellowship. Then in August, he managed to invite me in Oberwolfach. And after the talk in Oberwolfach, he said, okay, there is also the second half of the fellowship. Anyway, so I am really grateful to Volker because I could start my career thanks to him. But since my closest colleague when I was a physics student in Pisa is now the CEO of Ferrari, sometimes I think if Volker had not replied to my mail, my bank account balance would be probably astronomically different. So, but that's life now. 25 years later, it's too late. Anyway, so let's start. So I'm going to tell you about a recent paper with Jürg Fröhlich, Zhu Gang, that appeared in CMP. The title is A Theory of Quantum Jumps. So can I use a... Okay. So this paper is about the ETH approach or completion to quantum mechanics. This is an attempt to complete quantum mechanics. This attempt is by Jürg Fröhlich. He has been thinking of it since now 12 years. Disclaimer, you might wonder why you should listen to me rather than to the master. Incidentally, the slides are your slide. So, but I think there is something to gain because I did a big effort to understand. So maybe this might be useful, helpful for you. So instead, when your talks is maybe a little bit more difficult to pose questions and to say about why this is like that. So I did that, and maybe this can help. So this is the summary of my talk. I don't expect to tell about much about the last point, but let's see. I think it's more important to be clear rather than to cover everything. So I will start with a sketch of the ETH approach to quantum mechanics. Then I will present some non-relativistic model of matter interacting with the quantized radiation field that fits perfectly in the framework of ETH approach to quantum mechanics. And then in order to explain the stochastic law that we want to establish for the dynamics of individual quantum systems, I will review the heat equation as an equation related to simple random walks. This will be extremely, I think, helpful, this analogy, to understand how the Lindblad dynamics, which is a linear deterministic dynamics is related to random events or quantum jumps, as we call them. And so that's the plan. Now, so what we want to find, we want to find a law of dynamics for non-relativistic quantum mechanics. I mean, of course, the ambition is also to find a law of dynamics for relativistic quantum mechanics. But so what's the fundamental problem which is still open in quantum mechanics? If we look at charged matter interacting with the quantized electromagnetic field, electrons in the shell of an atom coupled to the radiation field, what we have seen in previous talks, we have that the dynamics is in fact nonlinear, dissipative, and stochastic, featuring isolated random events, sometimes called quantum jumps. So think of the spontaneous decay of an atom. These are random events. And the problem that we learn quantum mechanics according to the Copenhagen interpretation, so we know that there is a deterministic evolution governed by Schrödinger equation that at some point, okay? And we assume that the measurement is instantaneous, but in fact it's not. And the evolution, the measurement is clearly stochastic because of Boltzmann. Okay? So why we don't have a theory that somehow provides this evolution in a way, and moreover, it's not that these random events are only related to measurements. There is an opposite, because we believe that quantum mechanics covers nature before the appearance of human beings, and there are random events like the decay of spontaneous decay that okay, so we look for such a law. What? Because it's not linear. When yes, I could explain better with the black box, because maybe we can talk later about, okay? Because otherwise, but at some point I'll go to this point, and maybe I hope it will be clear why it's nonlinear. So, okay, so this will involve a new type of stochastic process that we call quantum Poisson jump process. So let's see what are the principles of this ETH approach to quantum mechanics. So the time evolution of average of states taken of a large ensemble of identically prepared physical system is linear and deterministic. Okay? And the equation that governs this evolution is Schrödinger or Greenblatt dependent. System is open. And this is the evolution of an average state that we call also ensemble state. But the time evolution of the state of an individual physical system is nonlinear and stochastic. And the ETH approach, for sure, provides, at least for non-relativistic quantum mechanics, for some models of non-relativistic quantum mechanics, provides this stochastic law. And it is based on the following 4 ingredients. So physical quantities are represented by a family of operators, abstract self-adjoint operators. At every time t, all the elements in this set OS are represented by concrete operators acting on Hilbert space. We consider always bounded operators, and they are self-adjoint, of course. And the time evolution of these operators is given by Heisenberg equations. Heisenberg equations are the, the starting point of any of these evolutions. Okay, we don't give up Heisenberg equations. Absolutely. Then we have algebras of potential events that are defined in the following way. So these algebras are given by, so C larger or equal than T is the algebra obtained as a weak closure of the algebra generated by these operators xt prime with T prime larger or equal than T. Okay? So by definitions, of course, we have that xc larger or equal than T prime is contained or equal to xc larger or equal than T if T prime is strictly larger than T by construction. And also because of Heisenberg equations, we have that these algebra are unitarily related by the time evolution. We consider the system autonomous, okay, by the unitary conjugation here. And the HS is the Hamiltonian of the system. So they are isomorph, these algebras. Nevertheless, these algebras, if this third ingredient, which is crucial, holds, are not the same. So the third ingredient is what we so before going to the principle I was referring to, I have to first introduce what are the events. Events happening at some time larger or equal than T, possibly happening. These are potential events, possibly happening at some time larger or equal than T, are given by partitions of unity by disjoint orthogonal projections acting on H. So these pi xi are orthogonal projections. Their sum is equal to the identity. The label xi run into a finite or countable set X. And this is a restriction that, however, is okay for quantum mechanics because of the fact that the states that we are going to consider are, because the algebra that we are going to consider is of type 1, so the states are density matrices, and the spectrum of a density matrix is discrete, okay? So that's the reason why we have this restriction, which is, however, completely legitimate in non-relativistic quantum mechanics. For the assumptions that I'm going to do later. Yeah. Now these are those are observables. So it's an algebra of operators, okay, with supports larger or equal than T prime. Think of space-time, okay, with supports larger or equal than T prime. The support is always considered compact. So an interval concerning time supported in an interval which is where the lower the lower extreme is larger or equal than T prime. Okay. Now so these are the events, and we say that an isolated but open system, so a system that can exchange information with the environment to infinity, is characterized by the property that the principle of diminishing or declining potentialities holds. That means that these algebras here are contained one in another. If T prime is strictly larger than T, C larger or equal T prime is strictly contained in C larger or equal than T. And this, in fact, is true in whenever we have an electromagnetic field, thanks to Huygens principle. And when I'll present the model, I will go back to that. And this is a crucial mechanism to have random events. So if we don't have this property, the system is closed and nothing really happens, and the evolution is always given by Schrödinger evolution. Okay. Now, so what is a state? A state of any of these systems or identical that form an ensemble is at time t is defined to be a normalized positive linear functional on the algebra C larger or equal than t. Okay, this is the definition of the state at time t. Is the restriction to that algebra. Now, if PDP doesn't hold, we have that all the algebra are the same, because we have a equality. And then we have that in Heisenberg picture, the state, the evolution of the state, according to this definition, is actually a trivial evolution, doesn't evolve. So what we learn in textbooks, that in Heisenberg picture, the state doesn't evolve. But if PDP holds, also in Heisenberg picture, the state evolves, okay? Non-trivially in time. Now, this is the assumption concerning the type of algebras C. So in non-relativistic QED, in relativistic quantum mechanics, these algebras are actually isomorphic to the algebra of bounded operators on a subspace H not of the Hilbert space H, so are of type 1, and the states for an algebra of type 1 are density matrices. Okay, now this is a little bit delicate paragraph, so I hope to be clear, and in case, please stop. So we start at time 0 with our state in so this is the state in Heisenberg picture. When you see the tilde is in Heisenberg picture. And so this is the state at time 0. So it's a state on the algebra C larger or equal 0. Okay, according to the definition. Now, because of the isomorphism, we know that when when we consider the evolution, the state remains a density matrix. But so now we want to know what is the state at time t in Heisenberg picture. So what is this state? Is just what you see here on the right-hand side. So we know that it's a density matrix, and this is the restriction of the state that we have at time 0 to the algebra C larger or equal than t, and all the elements of the algebra are obtained from an element in the algebra C larger or equal than 0 evolved up to time t, according to Heisenberg evolution. Then, starting from the right-hand side, we define what is the same state in Schrödinger picture. So it's defined here. is this density matrix omega t such that the trace of omega t x is equal to the right-hand side. So now, what's the point? That you can start from a state, a density matrix omega tilde 0, which is a rank 1 projection, a pure state. And of course, this omega t as a mathematical object is another projection in the Hilbert space. But this is not anymore a pure state for on the algebra xi larger equal than 0, because this algebra here is not the full algebra of the bounded operators in the Hilbert space. So you start from generically from a pure state, and you immediately get to a density matrix. And this is because of PDP. Okay? I hope this was clear. So now we will work in Schrödinger picture. No, it's not the full algebra. Because, what, sorry? See, on H naught, which is a subspace of H. Okay? No. This is still linear, and this is the evolution of the ensemble state, which is a linear deterministic. In the next slide, I'll clarify this point. So now, under certain conditions that we will see in the model, so concerning the initial density matrix omega tilde 0 or omega 0, at the time 0 picture consumption. Okay. So the evolution. Yes. Yes. This is explained by what I said before. It's nothing but. No, there is a trace, but so the partial is because you restrict, you look at this projection on the full Hilbert space as a state restrict to a subalgebra, not to all the algebra bounded. And then it's not the pure state. This maybe when I talk about the model, I'll explain what's the point. I think what you mean by partial trace. So so the omega, this is the in Schrödinger picture, under certain condition, we have that the evolution of omega is given by a semi-group of completely positive linear maps. Calligraphic L is the Lindblad operator. Okay, and this is a linear deterministic evolution. Then the next postulate concerns the evolution of individual quantum systems, and so this acting on density matrices. Wait, yes. So so now there is a postulate that says that the states at all times t of individual systems are always pure states. So they are finite rank orthogonal projections, pi t on H naught. And these pi t are random objects, and the nonlinearity enters. So this step, what in the evolution of individual quantum system, at some point, as we will see in the model, there is a random event, and there the evolution is clearly nonlinear. better explain on the blackboard mathematically, but I think it's clear that it's nonlinear. And this will be this random process will be obtained by unraveling this Lindblad equation there. Okay? And a generalized Born rules holds. Now, here I should say more about the general, because this is restricted to some special models, and I should talk about the same for the centralized state and so on, but it too absolute. Yes. And also how this unraveling and this stochastic process where nature selects one of these projections by T. So these are the projections that form an event. So a potential event, some event that becomes a network. And nature selects one of the projections of the potential event. So the new elements with respect to ordinary quantum mechanics are the principle of declining potentialities and the state reduction postulate as we in the general form, and as we will see in these models in a more specific way. So, yes. No, it's not, generically is rank 1, but it's not needed that is rank. And thanks for this, because later I will always consider rank. So they don't. So now I'll present the model. This model is a very simplified model of non-relativistic QED. Since there were several talks, I think emitted or oh, now there is an approximation, further approximation in these previous models. We consider the limit C to infinity. So what happens at C equal to infinity? C equal to infinity. So maybe start. And simplification. Let me complete the description with the Hamiltonian. The Hamiltonian is given by a matrix in Cn that describes the atom, this HA tensor identity, plus the Hamiltonian of the free field, plus an interaction, and an interaction is of this type, it's a linear interaction. Dij are matrices in Cn that have matrix elements Dij for if we consider states psi I, psi j, otherwise the matrix elements are okay. And these Cij are, of course, the wave function of the photons that have the frequencies relate to the absorption and the emission between levels I and j. So in this non-relativistic regime, we have that the algebras are then isomorphic to the bounded operator of the algebra C larger or equal than T, acting on these subspaces where we have only the subspace of the Fock space obtained applying creation operators, the vacuum with time strictly larger than T. Okay, and what? It doesn't change basically anything. So, and we can prove that the principle of diminishing potentialities holds. So, concerning the probabilistic law, so here the algebra support Which question? Yes, I'll repeat. Yes. Anyway, I want to say concerning PDP that the point is that the commutant associated with the algebra of the electromagnetic field supported in the forward light cone with vertex T prime intersected with the algebra of the electromagnetic field supported in the forward light cone with vertex T less than T prime is given by the algebra of the electromagnetic field operator supported in the diamond. Okay, that is given. I mean, I hope it's clear if you have in mind. Now, this algebra is clearly not abelian. So this implies that the algebra. This is a non-abelian algebra. So if the algebra with supported in the forward light cone with vertex T prime coincided with the algebra of the forward light cone with vertex T, we would have a contradictions because in the commutant of this algebra, there would be operators that do not commute. So yes. No, we are talking, we are working in 3+1 dimension. 3+1 dimension. So this mechanism also is preserved when we take the limit C to infinity. And so now we make this assumption that time zero, the system S is prepared in a state without any photons. And because of this choice, we don't have to deal with so-called memory effects, because all the emitted photons, because of the limit C to infinity, disappear as soon as they are emitted. So the system concerning the electromagnetic part remains in the state, in the vacuum state. So this is because if C equal infinity, any photons emitted times less than T have already escaped to spatial infinity at time T. So this fact allows us to entirely neglect the degrees of freedom of the radiation field, provided S is prepared in the vacuum state of the radiation field. Even if for this model, if I consider it as initial state density matrix, which is not concerning the electromagnetic part, the projection to the vacuum, I would not have a Lindblad equation. Okay, so that's just to warn you that this is a spatial choice where, however, we can control very well and show this stochastic dynamic law that we want to find out. So that means that now in a Schrodinger picture, our density matrix is just given by an omega t that concerns only the atom part and the projection onto tensor the projection onto the vacuum. And this Lindblad equation that we get applying applying the recipe that I said. So what is the state at time t? I take the state at time 0 and I restrict to the algebra xi larger or equal than t. So from this definition, we get what is the evolution in Schrodinger picture of the state, and this is given by this. So it's generated this semi-group by this Lindblad operator, where the VK are just a convenient way to rewrite this expression. So in this expression, you see exactly terms from the Hamiltonian. Now, in order to shorten notation, we write just the sum of index k of, and we call this VK star, okay? Now, unraveling this Lindblad equation will yield the law of the stochastic dynamics of individual quantum systems S. So this is the evolution of the ensembles. Now we want to find the evolution of an individual quantum system. And in order to understand this unraveling, now I will show this analogy. So I will start from the diffusion equation and random walkers, and this is for sure a very useful, helpful analogy. So let's consider a large ensemble, calligraphy C, of identical non-interacting random walkers. So this, in the analogy, then when we switch to the quantum case, the random walkers are replaced by individual quantum systems. Okay? Now, an ensemble state at time t is given by the density, rho t, of random walkers on the lattice Zini. And the time dependence of this density is governed by the diffusion equation, where this operator is just the discrete Laplacian. Okay? So delta is the discrete Laplacian, d is the diffusion constant, and this sum extends over all sides y that are nearest neighbors of x. By the way, how much time do I have? 9 minutes. Okay. So clearly the diffusion equation is a linear deterministic evolution equation for the ensemble state rho t. And this is the analog of the Lindblad equation of the previous. Now, a solution of equation 6, the solution rho t of this equation, is non-negative if at time 0 is rho t is non-negative. And moreover, this, let's say, discrete integral, the sum is independent of time, is very easy. It's enough to apply, to differentiate with respect to time and to exploit the definition of the discrete Laplacian. So we can normalize this rho t at any time. We have that this is equal, this sum is equal to 1. Now, we would like to understand what kind of stochastic motion of a single random walker omega implies that the time dependence of an ensemble state rho t is determined by the diffusion equations. For this purpose, we have to unravel this equation. How do we unravel the equation? We take the Lindblad equation and we write it in the infinitesimal form. Okay. So this is up to, so we have these terms up to order dt and the higher order. So now the true state of an individual random Volker omega at an arbitrary time t is a site that I denote by x omega t. So that a random Volker is always a given site. And this, so a random Volker is always in a pure state. And the analogy is that the individual quantum system is always in a pure state. Okay? And this state corresponds to a rho t, which is a delta function. So the state of a random Volker is a delta function. Now, during a time interval, t plus delta, a random Volker omega may remain at the site where it is at time t, x omega t, or can jump to a nearest neighbor site y. Okay? And this equation determines the probabilities for omega to remain at the given site, at the initial site, or to jump to a site y such that the distance for x omega is 1. How do we find these probabilities? We rearrange the equation, the previous equation, okay? And we interpret the coefficients in front of rho tx and rho ty as probabilities. So it turns out that rho t plus dt is a convex superposition of pure state corresponding to sites x omega t, rho tx, and x omega t plus delta, rho ty. The coefficients that appear in this superposition can be interpreted as probability. So we have that there is a probability of no jump from time t to time t plus dt, which is 1 minus 2 ni d. Ni is the dimension of the lattice. And these are the probabilities to jump to one of the nearest neighbors. Okay? Now, the sum of these probabilities, of course, is 1. And we can then calculate what is the probability not to jump in the interval t prime, t double prime, just starting from this infinitesimal probability here. And this is what we get. Now, we can construct clearly a measure and by calculating the probability that a random Volker traces out a given history, a history that means a given sequence of jumps. So here we consider that the random Volker makes n jumps at times tk, and from tk minus 1 to tk doesn't jump. So we have just to multiply the probability not to jump in this finite interval tk minus tk, and to jump in these infinitesimal intervals around tk. And so we get this expression. Then, of course, we can recover all the results that we know. We can show that the motion, the average motion is a diffusive one. So we have unraveled the diffusion equation, interpreted as a result of an average of stochastic motions. So we want to do the same for Limlat. So we have we start with all the systems, all the individual systems in the same pure state omega 0, okay? And this is a rank 1 orthogonal projection. And concerning the electromagnetic field, we are in the vacuum, and it will remain in the vacuum. Now we take the Lindblad equation and we write it in the infinitesimal form. Okay. Now, according to the ETH approach, the state of an individual system is proportional to some pi t tensor, the projection to the vacuum, where pi t is an orthogonal projection of finite rank at all times. This is what the state reduction postulate that I state beginning claims. Now, how these pi t are found is actually using, as before, rewriting now the density matrix omega t plus dt. We rewrite in terms of its spectral projections. So we know that we can write in terms of its spectral projections. We know that it is a non-negative operator with trace 1. I'm assuming as a simplification that all these projections are one-dimensional. Okay? And then what I have, that the sum of these coefficients, of course, is the sum of the eigenvalues, and has to be 1 because, yes, I'll finish. So because the trace is 1, and I can calculate, as before, what is the probability not to jump, so to remain in the same projections, but warning, this projection is also changing in time. This is something a little bit different with respect to the random walk, where there the state remains the same. Here is changing, but no jump means that the individual system remains in this pure state following its evolution. It doesn't jump to one of the other projections. And so in order to find how this evolves, these projections evolves in time, we use an application of Lichwinger that in an infinitesimal version that we call infinitesimal perturbation theory. But in the end, let me go to this slide to understand what happens. That now we have that the individual quantum system at time t is in the projection pi t that is following a trajectory that is given by this cubic equation. Okay. Now we have that remains in this pi t as long as, I mean, doesn't jump to another projection, and the probability not to jump is given here. So we calculate the probability not to jump from time 0 to t using perturbation theory. And so if it doesn't jump, the individual quantum system is in the pure state pi t that is evolving according to this equation. Then it may jump and goes to another projection, and then it starts again the process. So now, of course, we have that if the interaction is 0, so if alpha, the fine structure constant, is 0, if the system is a closed system, because it's not open anymore, and because cannot exchange information with the outside. And what we have that the probability not to jump is 1. And this equation here, of course, reduced to the usual Schrodinger equation. Okay, but in fact, the evolution is not generically is not Schrodinger. It's governed by this cubic equation, and this is a stochastic equation because we have an equation along with the probability that it will jump or not jump. Yes. Thank you.
Are there any questions?
Yeah, so so my question is, how is the I mean, this you had described this random walk
Yes.
As a comparison, yeah. So there's a
Yes.
Poisson process, and it takes values in, so to say, integer points,
Yes.
but it's actually a semi-group. So and here my question is, how do you choose here the, so to say, the lattice points? I mean, you start from some pi t, and what could then the state jump to? Well, how is it determined?
So here, I didn't have time. So here we can construct in the same way this measure, probability measure for each trajectory of states, because each individual system goes through through different jumps, and so it single out a trajectory of states, and we can, for the random walker, write what is the probability that sorry. Okay, so this is the analogous for our quantum system. We exactly like for the random walker, we compute what's the probability that is times t1 tn, the individual quantum system has jumps. Okay, and then of course, if we average over this over these trajectories with the weighted with these probabilities, we recover the evolution of the ensemble system. So evolution linear indeterminism, right, for the diffusion equation is reconstructed by somehow all these stochastic history of all the individual quantum systems. And this can be seen in a very clear way. Even better if we consider discrete nodes. It's, I think, a very pedagogical. We cover the evolution of the ensemble state starting from this isthmus. Okay. I didn't repeat the question.
In the microphone.
Okay.
Way of unraveling an in-band equation.
I mean, the decomposition is unique in using the spectral theorem. The composition into those projections is unique.
Yeah, but is there a unique stochastic equation? I don't know anything, so I'm just asking. Are you sure you found the right stochastic equation?
I hate to say that, of course, these equations have been already used.
Of course, yes.
Okay, so these are well known, and there have been many proposals. I think what Jürg Fröhlich somehow added to all this story is that this I really follow from some postulates. It's not phenomenological. So, of course, what remains to do is to test this with experiments. And this is what we are trying to do also with Carlo Albert and Jürg Fröhlich, to find, to propose an experiment where one can really see this evolution of individual quantum states according to this approach. Until that, I cannot say that is the true one, of course.
Maybe a related question. So you seem to have made many assumptions to make sure you have a Lindblad evolution. What is happening if you don't?
If you don't, basically, you have memory effects. So you have to consider, in order to know what happens at t plus dt, you don't have only to know what is the state at time t, but also in the previous times. And this is, yes.
One last question, if the chairman can.
So mathematically gets extremely complicated.
Okay.
Yes.
My last question is also,
but it still remains linear and deterministic.
So my last question is just to check whether I have well understood. So the stochastic events happen at discrete times. Is that correct or not? It's not like Brownian motion, which is
no, I mean,
it's only discrete times. And between this, is it what you explained, or is it really a real completely stochastic, like Poisson?
See, Poisson, discrete times, yes.
Discrete times, and then between the discrete times, then you have a deterministic nonlinear dynamics on this projection.
I mean, the projections evolves without jumping. Since in this sense, deterministic, yes. But there is a probability that, I mean, the equations comes along with the probability not to jump.
Of course, of course. Okay. Isn't it a little bit surprising in a way? Because if I think of the heat equation and Brownian motion, then it's not discrete terms. It's very random everywhere. No?
So you are concerned with this?
I don't know. I'm just asking.
I mean, you can reconstruct the Lindblad equation from these histories. That's true.
But maybe related to the first and the last question.
Yes.
I mean, sort of in the physics literature, there's also something they call unraveling with the background of numerics. Like there's this work by Møllmer, for example. And they end up with
please say it again, because
Klaus Møllmer from Copenhagen. They also do sort of unraveling of Lindblad equations and can prove that sort of, or you can prove was them, but you can prove that sort of averages to a Lindblad equation. Is there a precise or more or less precise point in the postulates of the ETH where you can sort of pinpoint what leads to a completely different unraveling in this case?
Unfortunately, I don't know that work, so I'm somehow new in the field.
That's something very continuous.
But I mean, concerning what you asked, in some sense, the analogy with Brownian motion comes for sure if the type of algebra is not one. So if we have algebras of type 2, because then the spectrum of the state is not discrete like for density matrices, is a continuum, and there are all the complications that we have in Brownian motion. But this is something actually that we plan to start to work on. Yes.
Maybe this question is too metaphysical, but
too many?
Too metaphysical.
Metaphysical, okay.
But imagining that in some hypothetical future we have managed to write down the Hamiltonian for the entire universe.
Yes.
Would we then, if we would then have a completely closed system, would that then be deterministic? Would it just follow or is this then, because you have the interaction with the fields, is that enough to get this sort of dynamics?
So there have been many attempts to explain with an Hamiltonian that includes all the universe. But all of them failed.
Yeah, what I'm really
So,
asking about
the
is
point-
if it
the
was a
point that
completely closed system but still had interactions, would you still have this type of?
If it is a,
I guess I'm describing a
I
completely
mean,
closed.
from here, it seems that if there is no possibility to release information to infinity with a mechanism that has on mathematically the effect to shrink the algebra, then you don't have random events. So, for example, if you screen everything with in a cavity, at some point you should not see any quantum mechanics anymore.
Any other
Of course, I
question?
cannot claim that we have proven that.
I have a question which is related to the random walk. You said that that when you have a time interval, that the random walk is going to be in a superposition of states in that interval. And I was wondering if you could elaborate on that because it's sort of in a jump, no jump state. So
Yeah,
how?
I mean, it's really something that we have to work out. So it's very, very, at the moment, unclear how to work on it. So when we don't have a discrete set for that label our projections, of course we have to consider some integrals of projections and but mathematically is for sure something because it's a stochastic process. So it's also, I think, very interesting because we don't think there is much about that done in the literature. So in some sense, a stochastic process which in the simplest formulation is like that, and in the more complicated one, we don't know yet how to deal with it, and it's somehow a new stochastic process to study. So maybe it might be interesting to probabilities irrespective of the physical motivation.
Any other question? Well, you mentioned the connection with the measurement problem. Could you add some comments on that?
The measurement problem.
You mentioned at the beginning the relation with the measurement problem.
Yeah, the relation, you see, we wrote a paper with Jürg Fröhlich before that. It's called the evolution of states in quantum mechanics, I think. I don't remember exactly the title. And there we consider a model similar, but even more simplified with discrete times. And we consider different type of interaction and different regimes for this interaction, weak, strong coupling. And in some sense, the strong coupling regime should mimic the measurement apparatus. And there you can really see, and I think this is something to develop and to improve. You can really follow the interaction, excuse me, the evolution, and see the evolution is for a while a unitary evolution, very close to unitary evolution. Then when the strong interaction with the apparatus takes place, so it becomes in the strong coupling regime even a Markov, like an evolution like in a Markov chain. So this has been done, but is very primitive. Okay. So it's something that should be, of course, developed, yes, improved.
Well, thank you.
But it seems that really one can one can really write a quantum mechanics where also the apparatus is treated quantum mechanical. Mm-hmm. And this scheme seems to show what one expects.
Okay, thank you. Any other question? Well, thank you again. This very beautiful talk. And we reconvene at 11:30.